Welcome to the orbits of planets and satellites. About 2,500 years ago, Aristotelian physics was believed to be correct. Ptolemy was also a Greek philosopher a few hundred years after Aristotle, and he presented the Ptolemaic model of the solar system. This is a geocentric model. Geo meaning the Earth, centric meaning center. So the Earth was in the middle of the solar system, and the Sun orbits around the Earth, as do all of the other planets. In the mid-1500s, Copernicus published his heliocentric model, and this led to the Copernican revolution, in which the Ptolemaic model was supplanted by this new heliocentric model. Copernicus had lots of good ideas, but there were several that still weren't quite right. So although he had the Sun in the center of the solar system, he also had the Earth orbiting in a circle with epicycles. So it would orbit, but it would do little loops every now and then. He also said that the Sun was approximately in the center of this circle, and that the speed of the Earth was constant. Kepler published some of his work in 1609, and he invented Kepler's first and second law. The first law being that orbits are ellipses, and that the Sun is at one of these foci. Here we have a diagram showing that the Sun is at one of the foci of this ellipse. An ellipse is a shape that's an elongated circle, and it has two foci. One here, and that describes the shape of the object. The Sun is located at one of these in all solar orbits. Kepler's second law tells us about the area swept out by an orbit. So here we have our orbit. It is highly elliptical, and we can see that during the same time, this planet is moving a greater or a smaller distance. That means that its velocity must be different at different parts of the orbit. But Kepler asserts that during the same time, the same area is swept out by these orbits. A few years after Kepler published this work, Napier, a Scottish mathematician, published his work on logarithms. This new mathematics was used by Kepler to publish his third law, in which he stated that the square of the time period of an orbit is proportional to the cube of the radius. In the late 1600s, Newton published his law of gravitation. He used Kepler's third law and was able to expand upon it further. Newton argued that the force holding the Earth in orbit around the Sun was the force of gravitation, and that it was also a centripetal force. We know that a centripetal force has that equation, And Newton's law of gravitation is this. If these two are the same, then we can write them as equal. We also know that velocity is displacement divided by time, and if that displacement happens to be the circumference of a circle, 2 pi r, then the time taken to move once around a circle would be the period. And we can now connect these equations together. And then rearrange this section for t squared. Those of you who are studying A-level mathematics will be perfectly capable of going from this equation to a log-log graph of t against r. However, those of you who are not studying A-level mathematics will not be able to do this. So I'm going to prove to you that a log-log graph of t against r forms a straight line. But in order to do so, I'm going to quickly review some of the laws of logarithms that were invented by Napier, and then use them to convert this equation. When we have a number with an unknown value in the power, but we know what it's equal to, we can access this number using a logarithm. Log to the base 10, there's our base. Log of n is equal to that exponent. So what a logarithm does is it takes an equation where you have a power, and it makes the power the subject of the equation. And there are some rules about the use of logarithms and how they work algebraically. If you can rewrite it as two separate logs added together. Notice that I've omitted the base, and we'll just assume that these are all base 10. If you have a number written to a power, then you can rewrite this as the power coming outside the logarithm and the number remaining inside. So we're going to use these two rules to rewrite this equation. We're going to take the logarithm of both sides of the equation. First of all. Then we're going to rewrite this side using this rule here. Now we're going to use the power rule to extract the 2 and the 3. And finally, we're going to distribute the 2 by dividing both sides by 2. That means that each of these terms will be divided by 2. We now have an equation in the form of y equals mx plus c. Y, these are all constants, so that is the value c. Here we have the x value, and here would be the gradient. If we draw this on a graph, where this is log t plotted against log r, we should have a straight line graph. The intercept, c, is a negative value, so the line starts here and stretches upwards. And if you plot the log of the period and the log of the radius for the planets in our solar system, then they plot along this line. You will not be tested on the derivation of this graph. You simply need to know that a log-log graph of period against radius produces a straight line result, and you should be able to sketch it, but you do not need to know how to arrive here. The reason I included this demonstration was for the benefit of those people who are also studying A-level maths. One of the other consequences of Kepler's laws is to do with the time and therefore the changing speed of a body as it orbits the sun. So we have this elliptical orbit, and what it means is that when you are close to the sun, your velocity is highest, and when you're further away from the sun, your velocity is slowest. We can see here in the same amount of time, a greater distance is travelled compared with this distance here. And this means that kinetic energy is at a minimum at this location, furthest away from the sun, and kinetic energy is at a maximum here. The total energy will be the kinetic plus the gravitational potential. So therefore, the gravitational potential energy must be at a maximum, the greatest distance away from the sun, and it will be at a minimum the closer to the sun that you are. And because the speed is slower, the further away you are, then if you were to extrapolate a circular orbit from that location, the period of the orbit would be largest, and if you were to extrapolate a circular orbit around this location, then the period of that orbit would be the smallest, it having the greater velocity. You may need to compare the orbits or consider differences when moving from one orbit to a new orbit. Usually, when objects are launched into space, they begin at the surface and then a rocket propels them higher and higher and higher. There are usually several booster stages where a more powerful rocket or one that has been replenished with more fuel takes over, and they get higher and higher and then fall into their orbital pattern. That's usually how we get things into orbit around the Earth. But you need to be familiar with the concept of escape velocity. And that is, an object is launched with a single push up to a velocity. And that velocity is enough for it to continue and escape the Earth's gravity. Let's consider the gravitational potential. An object on the surface of the Earth, in order to escape the gravity of the Earth, would need to climb out of this well and reach a distance of r equals infinity. And if it escaped at exactly the escape velocity, then it would reach this distance with a total energy of 0. It would start off with kinetic energy, and that kinetic energy would reduce as it gets higher and higher and higher, eventually reducing to 0 at the point whereby it can be said that it has completely escaped the Earth's gravity. As it climbs higher and higher, its gravitational potential energy increases, while its kinetic energy is decreasing. Recall that this is the 0 line, and therefore everything below here has a negative gravitational potential, and therefore the total energy it has would be 0, and the radius is infinity. This total energy is composed of a sum of the kinetic and the gravitational potential energy, which has a negative value, and therefore this is true. We have another way of expressing this in terms of the law of gravitation. If we rearrange this, we get recalling that this is equal to 0, and rearrange for velocity, we get, so the escape velocity, which is velocity required to escape the Earth's gravitational well and arrive at r equals infinity with 0 energy left, is equal to 2 big G times the mass of the planet you're escaping divided by the radius that you begin at from the centre of the Earth, square root. You need to be able to derive this yourself. This equation is not provided on the datasheet, and you may be expected to demonstrate how to arrive at this equation. Let's now look at different types of orbits. Here is a picture of the Earth, and here is the axis of rotation, which is inclined. We have orbits that go across the equator, which are called equatorial orbits. We have orbits that go directly over the poles, which are called polar orbits. We have other orbits that are defined by the time it takes to circle the Earth. Those that circle the Earth once every 24 hours are referred to as synchronous. Or sometimes geosynchronous. And then there are those orbits that go around the equator and have a period of 24 hours. That means that if you are on the surface of the Earth and the satellite is directly above you, then a short time later, the Earth will have rotated and you will have moved, but you can still look up and see the satellite directly above you. the satellite is rotating around the Earth at the same rate that the Earth is rotating. This is known as a geostationary orbit, and it only works if you have an orbit of 24 hours above the equator. One important thing to note when discussing satellites is that typically the altitude is given. And the altitude is the distance between the satellite and the surface of the Earth. If you are doing calculations involving radius, for example, let's say that you're using the equation that comes from Kepler's third law, then you will need to make sure that you're using the radius, which is the altitude plus the radius of the Earth. One very famous orbiting body is that of the International Space Station, or the ISS. It has an orbital period of approximately 90 to 93 minutes, and it is in a low Earth orbit at an altitude of approximately 400 kilometers. Notice that I say altitude and not radius. The orbit is approximately polar, but not quite, and it rotates around the Earth once every 90 minutes. That means that when it is in this position here, the next time it is in that position, the Earth beneath will have rotated by the amount that it does in 90 minutes. The result being that the ISS can cover virtually every part of the surface of the Earth. The altitude is so low that the ISS can be seen with the naked eye from the surface. Here is an example of somebody's observations from their garden here in the UK. The ISS reflects sunlight, and it can be seen moving across the sky. Here is a diagram showing some of the more famous orbits. We can see the ISS over here in a low Earth orbit, very, very close to the surface of the Earth. The Hubble Space Telescope is also in a low Earth orbit as well. Here we see the geostationary orbits, which are extremely far out. And one interesting thing to note here is the graveyard orbit. When a satellite has reached the end of its life, it is pushed out 300 kilometers beyond this geostationary Earth orbit so that it doesn't collide with any of the active satellites that are still orbiting the Earth. Here we can see on this diagram that we have axes that show the radius of the orbit as well as the orbital period, because the greater the radius, the greater the period of the orbit. And we can see speed as well, because the further out the object is, the larger the circle it needs to describe, and the larger the speed. There are many different names on here of different types of satellites that you may wish to research.